Yeah, I'm very proud to also introduce my younger colleague, Carmen Almudever, because it's important that it, as you will hear and as we heard also from the previous talk, it's a new field and we still have like 99% of things to discover actually. So I'm very glad that I have been able to motivate younger people, and she's one of them, to join in this research. So as we said, so we are part of the electrical engineering faculty, but that faculty together with the physics faculty at the university, they decided to actually jointly set up a quantum research lab. It's called QTech, and the main inspirator of that was Leo Kouwenhoven, and he is working, or is currently still working on Majoranas, which we will not talk about because that's really counterintuitive. Yeah, even though it's extremely important, most likely in the future. So we are belonging to what is called the fault-tolerant quantum computing network, and therefore we work primarily with physicists together. And so what we'll be talking about is nothing very similar to what you're doing, yeah, but it's a bit of a higher level. It's really at the computer architectural level, and I hope that we'll explain those things. Oh, okay, here it is. Yeah. So this is basically the content of what we'll be talking about in, let's hope, yeah, within the time that is scheduled for us. So it's about what is the difference between classical and quantum computing. We will talk a little bit about, yeah, what those quantum gates are, because that's the really key, yeah. And I understand your point of view, but if you want to really exploit the power, the potential power of quantum, you need to implement those gates. And so Carmine will say something about the power of quantum computers and quantum error correction, because quantum devices and quantum phenomena are extremely fragile and have extremely long lifespan. Yeah, so we're talking about nanoseconds. Yeah, that in transmons that the superconducting qubits that we're working with. Yeah, that's the kind of lifespan they have. So how can you make non-erroneous calculations in such a short time span? So there are techniques called quantum error correction that you need on top of everything, and that suddenly makes the entire machine explode in number of quantum devices that you actually need. Then I will come back into the talk and explain a little bit what then we assume a quantum computer is all about. And I'll just go one slide back. We have started a collaboration with Intel, and we all know Intel, and I'm sorry to say that within the ARM Research Summit, yeah. But ARM, we also hope that ARM will get involved into the quantum computing, and this is like an open invitation because we have a flagship on quantum that will start, to which the first calls will start next year. So we really hope that we can find 2-3 smart people at ARM, yeah, and I guess they are here, yeah, that would like to join us in this endeavor. Now, Intel, it sounds a bit like bragging, but nevertheless, we are proud of that. So Intel only decided to work with the team or the teams in Delft to develop what is now the architecture, let's say 5 to 10, and we're reasoning in 10 to 15 years, but we have like a times horizon of 10 years with Intel, where we hope to have solved all of the major problems, and that they can then internalize it, and that's why it's an open invitation to ARM, yeah, that they want to internalize the effort and start building their own commercial quantum device, and then maybe put it in the market, let's say in 15 years from now. So that's kind of the timeline that you still need to have before you can actually expect any kind of real result. So how does this, where does the idea of a quantum computer comes from? And we should not be surprised that it actually came from a physicist, yeah, namely Feynman, who in the early 80s made the statement that in order to be able to fundamentally study and understand what, in this case, quantum mechanics and quantum physics is all about, he said we actually should build a computer that uses, that operates along those functions, and then we're able to actually simulate whatever algorithm or phenomena that we want to study into the nitty-gritty detail on such a device. So he was the actual inventor of the idea of the notion of a quantum device. So that's like a couple of years before he died in '88. So yeah, of course, we cannot talk about physics without talking about Newton, right? Where we are now, where it was actually working. Now, in order to understand a little bit what now this quantum is all about, and so that's why I'm going to raise the level of abstraction a little bit here, is that we would like to explain a little bit the difference between a classical bit that we all know, of course, and then what is a qubit or a quantum bit. Now, we all know that the classical bit either has a 0 or a 1 value, and it can only be in either of those states at the same time. Yeah? So it can be either a 0 or a 1, but never any combination between the two. What is important with the quantum bit is that you can be a 0 and a 1 at the same time, according to a certain probability distribution, and this is represented by these alphas here that represent the amplitudes, and we will not go into those things, but if you rewrite those amplitudes in this particular way, and so you add the square root of the absolute value of these alphas, you end up with 1. And that means that the state of my qubit is always together in this 0 and 1 state, but together they're always they have the probability of 1. Now, what is the problem now, however, is that you need to measure them, because once you want to compute something at the quantum level, you need to know, of course, that's what we do classically, is you read the memory location, say, hey, this is the result. Now, if you do that at the quantum level, you basically you destroy the superposition state. So the superposition is I have a combination of the 0 and the 1, and if I want to read out the value, I'm simply going to have a random choice, like it's going to be either a 0 or a 1. So it's kind of, and that's why my predecessor, Stamatis Vassiliadis, he was always opposing to getting into quantum. He said, yeah, it's non-deterministic computing. Who wants to do that? Yeah, I don't believe in it. Well, the university and the Netherlands, they decided that it merits more research. Yeah, so this is a key thing that, and now my pointer is gone. Yeah, okay, so I'll try the red one. Okay, yeah, we still see the red one. Yeah, so the measurement is a crucial component of any computational device, because you need to read out the result. And the non-deterministic aspect comes from the fact that I'm going to compute with a large number of qubits, and then I will also need to measure out the qubits, and I'm leaving out here entanglement a little bit here, because that's a fundamental proposition also, or feature that you have in quantum. Yeah, so I need to measure out, and then what basically you do is you will find the qubit result, with the highest amplitude, because that's what quantum algorithms actually do. They do other gates than the adders and whatever it is. They do Hadamard, they do the T gate, the S gate, they do the C0 gate, whatever it is. Yeah, and that all that implies that you're manipulating those amplitudes, so that at the final version, when your algorithm is ending, you want to read out what your result is. Then you will read out that state of your qubit with the highest probability, and that also means it's non-deterministic. So you may have to run it like 10 times or 100 times, and then you average out all of those readouts, because it's never like a single shot, because the single shot can give you maybe the wrong readout, because even if it's 10% of the cases, you will read that value in 10% of the cases. So you need to have, let's say, 10 or 100 readouts, and then you will get the right result, because you average out what those final results are. So those are two key elements. So what is another interesting aspect, that, and again, Carmen will say a little bit about that later on. Whenever I apply a gate, so here you see it's black or white, and here it's kind of grayish, from white to some black, because you can be anywhere on that stack basically, and depending on what the amplitude is, you're going to be either more oriented towards the black or towards the white. So whenever I'm applying a quantum gate, be it a Hadamard or be it a C0 or whatever it is, I'm applying it at the same time on this qubit, so meaning on the superpositions of that qubit. Now, how many superpositions can I have? If I have one qubit, they have two possible states. If I have two qubits, it's going to have 4, so it's 2 to the power 2. If I have 3, it's 2 to the power 3. And so it's always 2 to the power n which are the number of states that I'm manipulating in one shot with one gate. I'm always applying them on 2 to the power n actually qubit states. So quantum physics gives me massive parallelism for free, and for free we already know that that's not true, right? But anyway, that's the great potential of where quantum physics is all about. So these are examples of these quantum gates, the Hadamard, the T, and the S gate, yeah, and they're basically, yeah, there are some mathematical operations or conditions that you need to apply. But an important one is that maybe this one, that's kind of different from, let's say, classical computation, where we have like a forward mechanism in the execution of all of my classical gates. But when we do quantumly, quantum is always reversible. I can go to the right, but I also can go to the left. I can go back and forth in time, basically, so to speak. Yeah, and that creates a completely different way of reasoning about how such a machine should also be built. So these are just the examples, yeah, of Hadamard gate, the T gate, and the S gate. Yeah, and again, we will not explain those things, yeah, because we did organize, and we're maybe planning next year at Micro to do it, yeah, a quantum tutorial for computer engineers, because we're computer engineers, yeah, we're not pure software people, we're definitely not physicists. So they say, you're an engineer, yeah? So we say, yeah, okay, thank you very much, yeah, that's what we accept to be. Yeah, so this is the classical universal gate. So this is the table for the NAND gates, yeah, and we do something similar here for the quantum gate. So here this is non-reversible, yeah, so it goes in one direction only, and here it can go always in two directions. And that's also one of the key things that makes quantum so extremely powerful, because you in principle, you never lose information. Well, never. That's not true. When you start measuring it, then suddenly, bam, yeah, you only end up with one result out of the so many 2 to the power n that you've been computing. But that's a separate. So when you look at a circuit, again here on the left, you see the classical circuit that we all know and that we pretend to execute. Yeah, and here is a quantum circuit in which you see that this is the sign for a Hadamard. This is a C0 gate. And the direction again is also always from left to right. So this is the teleportation circuit. We will not explain that, right, Carmina? Yeah, and if so, I always have to look at her because she's a specialist in those things. So yeah, so this is a bell pair, and these are then all kinds of additional steps that you need in order to say, because teleportation means I'm going to send this to a different location, but I will not send it, yeah, let's say, in a physical way that there is a path to reach my end. So it's only in an indirect way that I'm capable of doing such a teleportation. And in the end, you only ask yourself, did any error occur? Yeah, an X or a Z error, yeah, which Carmina will explain in a couple of minutes. Yeah, and then in that way you can actually transport the Q0 state to the Q1 state, yeah, by simply asking yourself at the end, do I have an error or not? And if yes, I only have to apply a certain correction, and then I have the Q0 state in the place of where the Q1 is actually. So that's I will also give references. We will give references at the end of the talk. Yeah, we have developed. So that's one of the things we have to do, right? Yeah, is a QX simulator. Now a simulator that's open source. Yeah, so you can download the source code, you can download the executable. Yeah, you can start experimenting with it yourself. We have some exercises also to go along, so you can execute all of these circuits, and of course many more complex circuits on this QX simulator. And again, there you see that the largest simulator that was ever developed, yeah, I'm sorry, it's in Delft, which is ours, because it can go up to 49 qubits doing full universal simulation. That means you can basically apply any kind of quantum gate on it, and then you will get the correct result. Yeah, so that's an achievement that we did. So I already spoke about the combination of qubits, yeah, which is entanglement. So again, this is the classical case where we're combining 3 bits, and it's either a 0, 0, 0 up to the 1, 1, 1, but it's always going to be one of those combinations at any point in time. In quantum, it's all of those things at the same time, and then you apply a gate on it on all of those, in this particular case, eight states at the same time. So if it's 2 to the power n, that's where your exponential growth comes from in the quantum. So it's superposition, and then entanglement, we drop it for now a little bit because that's a specific way of combining those gates. And basically, it boils down to having specific amplitude values, yeah, which you cannot simply decompose into underlying ones. So it's either this or okay, okay. So this is where the exponential power comes from. Yeah, I'll simply say by adding 1 qubit, yeah, you each time double the amount of computational power that you have. Now, the only thing that we want to show here is that quantum computing is actually a way to spatially compute, because you have your qubits, which are then each of those knots in this graph, basically, yeah, and then you're going to apply those functions f1, f2, f3 on those qubits. So it's a really in-memory computation, so you want. Okay. So now, Carmina, you say something about.
So yeah, so quantum computers can be more powerful than classical computers. In other words, can solve problems that are intractable, but even the most powerful supercomputers. So what those problems are? So they are good at solving some optimization problems, like the well-known D-wave, that it's focused on optimization problems. They are good at big data. They are good also, for example, at some applications of molecular simulation or even for synthesizing new drugs. These applications here, it's believed that in the next coming years, I'm saying like 10 years, we will see some of these applications in quantum computation. And also the most famous example is for encryption, decryption. So in this application, what you do is a factorization of a large number or decomposing its price number. And for that, what we use is what is called Shor's algorithm. This Shor's algorithm is exponentially faster than the classical counterpart. So let me focus on that. So imagine that we have, as I said, this encryption decryption. It's about factoring large numbers. So imagine that we have a 2,000-bit number. And for that, we want to use one of the most powerful supercomputers that is in China. And we built a data center as big as Germany and the Netherlands together. So if we do that, and we want to factorize that 2,000-bit number, we will still need 100 years. We will consume all this energy, all this money, and consume all energies of the Earth in 1 month. So if you want to solve the same problem, to factorize this 2,000-bit number using a quantum computer, you can do it in a bit more than 24 hours, in a bit more than 1 day. But how big is going to be this quantum computer? So how many qubits will I need for factorizing such a large number? So in this paper from Van Meter, it's mentioned that you will need about 5 billion of qubits. So why do we need such a big number of qubits? As Koen mentioned, the point, like, those are the good news, right? Quantum computers are better than classical computers solving some problems, but qubits are very fragile. That means that they lose the information just because of the interaction with the environment. So that superposition disappears just with interaction with the environment. So that this is called what is a coherence time that can go from the order to microseconds, for example, in superconducting qubits, to the order of seconds, like in MB centers. But what it gives you, it's a very high error rate in your operations. That, for example, in quantum, we have error rates to 10 to the minus 1, 10 to the minus 2. That if you compare with the MOSFET, yeah, it's pretty high. So how we build, how we do reliable computing using quantum computing. So what we apply is quantum error correction. Quantum error correction is par in classical error correction, but there are some limitations. But for example, in classical error correction, the first thing is that you do is you encode your bits. We use the same encoding in quantum computers. So you encode your physical qubit in what is called logical qubit, that is composed by several physical qubits. But the point here is like you cannot copy quantum information. So that's one limitation. The other thing is about detection. In classical computing, you do in classical error correction, what you do is majority voting. So you read out your information, and through majority voting, you see if there was a bit split or not. In classical computing, in quantum computing, as Koen mentioned, when you read out information, you destroy the superposition. You cannot directly read the qubits. And the other thing is like in classical computing, we only have bit flips, and those are discrete errors. And in quantum, we have continuous errors. But using quantum error correction, we can discretize them to bit flip and phase flips. And we only have 1 minute. So
yeah, we'll take a bit more than 1 minute. I'm sorry.
Okay, you took my time. Sorry, I can't leave it. Okay, sorry for that. Yeah, time over. Okay, we don't want questions. We can talk afterwards. Okay, so why? Okay, yeah, I was like, whoa. Okay, let me explain a bit how quantum error correction works. So the first thing that you do, as you do in classical, is you encode your physical qubit. So this is your physical qubit, and you encode in a logical qubit. I'm going to take this example. This is called the 3-qubit bit flip code that can detect and correct single bit flip errors. So again, you have your physical qubit, and when you build, it's a logical qubit that is composed by 3 qubits. So this is your state. For encoding, as I mentioned, you cannot just copy information because that's not allowed in quantum. And what you do is you take 2 more qubits that you prepare in the 0 state. You do these CNOT gates. Those are just 2-qubit gates between them. And then you get that state. But imagine that something happens. There is a bit flip there. How you are going to detect that there is an error in your logical qubit. So you say, OK, I just do measurements. OK, that's not possible because measurement destroys information. So you cannot directly read out your logical qubit. So how do you do detection? So again, you encode your physical qubit into what is called logical qubit that is composed by 3 physical qubits. Then something happened. And in order to detect if an error had happened in that logical qubit, you use what is called ancilla qubits. Ancilla qubits are helper or extra qubits that are prepared in the 0 state. And then what you do is what is called parity check measurements. That again is this kind of gates between these qubits. What they do is a parity check between the first 2 qubits and between the last two qubits. It's just a parity check between the first 2 and the last 2. And then by measuring them, you can see if there was an error or not. So in other words, if the qubits are the same, there is no error. If there are different, there was an error there. So when you measure these ancilla qubits, when you get, again, it's a binary measurement result, so either 0 or either 1 or +1 or -1, that, for example, you can build this kind of lookup table. It was, okay, if both are 0, if the measurement outcomes of both ancillas are 0 or +1, nothing happened. If there is, for example, here 0 and 1, it means that there was a bit flip in qubit 3, and then you have to apply that correction. All these zeros and ones here is pretty simple. It's just a lookup table. But all these zeros and ones are sent to classical electronics where the decoding process takes place. The decoding means to identify what error has happened. So what kind of error and in which qubit. And then you apply the correction. So this is a very simple code that I show just to illustrate the basis of quantum error correction. But the code, that one of the most popular quantum error correction codes is what is called surface code. In surface code, we have this kind of a structure. So the white qubits are my data qubits, or the qubits that store the information, and the red and green are my ancilla qubits. So the qubits that are used to do these parity check measurements or detections. Here we can see 2 kinds of qubits, Z ancilla and X ancilla, that are used to detect pre-flip errors and phase flip errors. So what you do is just to run these circuits, doing one ancilla, do the parity check between 4 data qubits, and again, you measure them out, you measure the ancilla qubits, and you get a big set of +1 or -1 that they are sent to your classical electronics in order to be identified. And for that, we use what is called minimum weight perfect matching algorithm, that is just a graph algorithm. Okay? And yeah, now, Koen again, we're late.
Yeah, we're late, but yeah, I mean,
yeah, anyway.
We can cut it here if that's what you want, and we can stop here. Yeah, or we can say something about the architecture now, which was the initial approach. But we had also the paper now that was accepted at Micro, so we had to kind of switch the content of the talk. So that's. So anyway, what is the underlying technology in physics? Yeah, we will not talk about them. 4 of them we do in Delft. Yeah, and only 1 in ion traps is done in other places. So we personally work on superconducting, yeah, as well as the quantum dots, so the spin qubits. And we start working on let's say, the NV centers too. So now, okay, we start recognizing things now a little bit, yeah, because that was the first thing we did, yeah, when we, years ago, they told us, like, define a quantum architecture. I said, well, okay, yeah, but the quantum architecture, in a discussion with a physicist, a surface code kind of thing. It's a two-dimensional layout of qubits. I said, but this is not an architecture, right? So anyway, we started by defining again what are the different layers that we classically see, and then we put a Q in front of each of those things. Say, okay, we're done. Yeah, yeah. And actually, it turns out that we are indeed not so far away from that particular idea. So what else do we, or what is another way to view our big picture? Is that yes, we have developed our own language, which is called OpenQL. I don't know. Yeah, okay, red again. Yeah, OpenQL, which is like OpenCL or something like that. Again, it's open source. It's freely downloadable. You can use it. Yeah, and it produces a QASM. QASM is quantum assembly language, which was originally produced by Chuang and Nielsen when they wrote their famous green Bible on quantum computing. Yeah, and that's and we're now in the work of standardizing that language and really making it a full-fledged quantum language. So which should at this level still be hardware independent. And then we are actually targeting different kinds of underlying devices. Yeah, so the transmons, the spin qubits, and the NV centers, which are on our horizon right now. So we already have developed now an architecture for the spin qubits and the spin qubits and the transmons. And yes, we try to see what is similar and what is different. So we are, we'll show, no, we may not show it now, yeah? That we are capable of actually writing something in OpenQL and then compile it to a spin qubit or to a transmon processor. So we demonstrated, actually re-implemented now the architecture that we see. And again, similar to what earlier was described, the physicists, they work in the pink box. Yeah, so that's something that's it's a closed box. So we don't talk about that because that's where the physicists with their, different kinds of brain sets are there. Yeah, and this is where we are. Yeah, we're basically in the blue. The blue is the classical digital control electronics. And then again, I will not explain everything too detailed, but one term in your talk was accelerator technology, and this is true. When you want to build a quantum computer, you're basically building a quantum accelerator, like an FPGA, like a GPU. Oh, it's going to be a quantum device that you can connect to a classical machine, yeah, which we have not detailed here. And this is then the logic that we think for now, yeah, we think we need, yeah, which is like a quantum instruction cache, the quantum symbol table. So you have a variable, yeah, which is a qubit variable, and you need to assign it at some point to a physical qubit. Well, that's done here. You also have logical qubits, yeah, which we kind of explained, yeah, very rapidly, yeah, during Carmina's talk, because you need to encode, yeah, you need physical qubits to encode one logical qubit. Then there are various ways, yeah, you need this cycle generator, which is the CNOT dance, yeah, the CNOT, yeah, between the ancilla and the data qubits, and there are different ways that we're not gonna explain now. But an important concept that we introduced is again a classical thing, microcode. Yeah, sure, every processor, yeah, has microcode. So why would we not use it also for a quantum? Yeah, so we get an instruction here, which is then decomposed into the corresponding micro instructions, and then it's being decomposed again into the micro operations, and then from the green box on, it goes into a deterministic execution. So here there is no variance in any timing. So if it's every 5 nanoseconds, that's when something would happen and has to happen. Here it's kind of more flexible because we need to do more reasoning. Yeah, so from here on it becomes deterministic, and here also this is where it's a code word triggered pulse generator, because in the end, yeah, your quantum device is an analog device, and everything here is digital. So you need to convert, yeah, what pulse, yeah, you need to define what pulse, and then make all of the necessary transformations from digital to analog. Now, well, the original the original content that we wanted to first present today was actually written now in this paper, which is now going to be presented in 1 month from now at Micro. Yeah, and this is one of the versions. This is an implementation of a real working quantum transmon processor. Yeah, so we have all of these things implemented. Yeah, and again, it's the same kind of logic as I failed to explain a bit clearly. Yeah, Again, this is like the setup, the experimental setup. Yes, and then you will kill me. I know. Yeah. So this simply says this is what we developed. This is FPGA. This is the Transmon chip. Yeah. This is the fridge, because we have a huge fridge which is about my size. Yeah. That's cooling this thing up to millikelvin. Yeah. And that's how you then control. And again, similar to your talk, we have all of the control mechanisms. But basically, the logic is here. We don't do anything manual anymore. Okay. Now, this is the movie that I did not want to show. Yeah. And so I'm going to conclude. Yeah. Okay. So we are indeed gaining in maturity, but the killing application is not known yet. Yeah. We still need engineering, and that's where we come in. Of course, everything will fall or stand with quantum error correction, as Carmina already explained. And what our ultimate goal is, yes, I'm sorry, and then it's my 5 last seconds, is to arrive at a tiled architecture. This is one tile in which you recognize again the different layers, and then we want to be able to connect many of those tiles to arrive at the scale that we need for a quantum device. Thank you very much for your attention.